So today let us discuss about excess thermodynamic functions. Excess thermodynamic functions. The concept of excess thermodynamic functions are used to show the deviation from ideal behavior. Okay, so deviation of real systems from ideal systems can be well expressed by using the excess thermodynamic functions. The deviation from ideal behavior can be best expressed in terms of excess thermodynamic functions. And we know what is the difference between say ideal systems and real system, or ideal gases and real gases, because in ideal gases there are no intermolecular interactions, right? So this excess thermodynamic functions that shows or that expresses the deviation from ideal behavior from the real behavior, that gives a better quantitative data about the nature of molecular interaction. Okay, so actually excess thermodynamic functions are used to study the thermodynamic functions of mixing. Okay, so it deals with the difference between the thermodynamic functions of mixing for real system and the corresponding value for an ideal system at the same temperature and pressure. Okay, so what is thermodynamic excess function? For example, if we are considering volume of mixing, right? So we have to consider volume of mixing of the real system and volume of mixing of the ideal system. And the difference between volume of mixing of real system to volume of mixing of ideal system is expressed by thermodynamic excess function. Okay, so the difference between the thermodynamic functions of mixing for a real system and the corresponding value for ideal system at the same temperature and pressure. Both measurements should be done at the same temperature and pressure. It is called as thermodynamic excess function, and it is always denoted by using a superscript E. So whichever is the excess function we use, we write superscript E. For example, if it is volume, we write V superscript E. Okay, in general we can write it like YE. So this quantity YE represents the excess, positive or negative. It can be, the excess function can be positive or negative deviation, right, of a given thermodynamic property of the solution over that over the ideal or reference solution. Okay, so when we compare it with the ideal or reference solution, how much it is excess, whether it is higher or lower than the ideal system, that is represented by this concept of excess thermodynamic functions. So how can we represent it? YE, excess of any thermodynamic function, is equal to mixing, like that thermodynamic function during mixing in the case of real system minus change in the thermodynamic function during mixing in the ideal system. Both has to be measured at same temperature and pressure. So Y is equal to delta Y mix real minus delta Y mix ideal. I hope this concept is clear, where Y can be taken as any of the thermodynamic function. Okay, so it is the difference between thermodynamic function of mixing for a real system and the corresponding value for the ideal system, and both measurements done at same temperature and pressure. Now we are going to see the expression for excess thermodynamic functions like excess chemical potential, excess free energy, excess entropy, excess volume, excess enthalpy, etc. Let us see each of them. Okay, so first let us consider excess chemical potential. That can be represented by using the symbol for chemical potential mu E and the excess E symbol, right? Mu superscript E, mu E. So we have we can write this for ith term mu I E is equal to mu real minus mu ideal, right? Okay, so for mu real we can write mu I 0 plus RT ln AI. Since it is a real system and we are considering it, expressing it in the terms of concentration, we use the term activity here. So mu 0 I plus RT ln AI minus, for the ideal system we can write again mu I 0 plus RT ln XI. For ideal system we can directly use the mole fraction term. And here mu I 0 plus this AI can be written as activity is equal to activity coefficient into mole fraction, right? Activity can be given as activity coefficient into mole fraction, because activity coefficient gamma I is AI by XI, right? Okay, so we are substituting activity, this term by these two terms, and we have splitted it up. Okay, so we get mu 0 I plus RT ln xi plus RT ln gamma I minus that for the ideal system we are writing it as such, mu I 0 plus RT ln xi. This mu I 0 value in the case of real and ideal systems are the same because it is a reference state, right? Then this RT ln xi, RT ln xi cancels out. Then what is left? Only RT ln gamma I, where gamma I is the activity coefficient. So X is chemical potential mu E. For ith component mu I E can be given as RT ln gamma I. Remember this equation. So the standard state of the components in ideal and non-ideal state have been taken as the same as I told you. Mu I0 real is taken as mu I0 ideal, so that we could simplify that equation into mu IE excess chemical potential mu IE is equal to RT ln gamma I. Okay. Now let us see excess Gibbs free energy, the expression for excess Gibbs free energy. How can we represent that? The symbol for Gibbs free energy G with the superscript E, right? GE. So GE will be equal to delta G mix in the case of real system minus delta G mix in the case of ideal system. And we know the equations for delta G mix, right? So it can be expressed as RT sigma Ni ln AI. We are representing it in concentration terms, so we use activity here. RT sigma Ni ln AI minus for ideal situation RT sigma Ni ln Xi. Mole fraction can be written directly. Let us take this RT outside because it is a constant, a common factor. So RT into sigma Ni ln AI. This AI can be substituted by Xi gamma I, right, as we did earlier. So we get sigma Ni ln Xi plus sigma Ni ln gamma I, and now we have to write this term minus sigma Ni ln Xi. RT is taken out here, right? So we have two terms, sigma Ni ln Xi plus and minus cancels out. So we have excess Gibbs free energy GE is equal to RT sigma Ni ln gamma I. Okay, so this is the general expression for any term. And imagine our system is a binary mixture, then we have to consider two constituents, 1 and 2, right? So this equation can be expressed as GE is equal to RT into, instead of sigma Ni ln gamma I, we can write N1 ln gamma 1 plus N2 ln gamma 2. If there were three components, it will be G is equal to RT into N1 ln gamma 1 plus N2 ln gamma 2 plus N3 ln gamma 3, like that. Okay, so remember this expression, excess Gibbs free energy GE is equal to RT sigma Ni ln gamma I. Now let us see how to find out excess entropy. Excess entropy can be represented as a superscript E, right? SE. And we know dG is equal to VdP minus SdT. When pressure is constant, dP is 0. So dou G by dou T at constant pressure will be equal to minus S. We did that to get the expression for entropy, right? So yes, when it is excess function, SE is equal to minus dou GE by dou T. We did it in this way because we already know the expression for excess Gibbs free energy. We can just substitute without doing all these steps. Okay. So S is equal to minus dou GE by dou T. So we can write minus dou by dou T into value for GE, right? Minus dou by dou T of this term RT sigma Ni ln gamma I. So we are differentiating it with respect to dou T. So this becomes unity, and we have minus R sigma Ni ln gamma I. We directly obtain the expression for excess entropy, right? Minus R sigma Ni ln gamma I. So SC is equal to minus R sigma Ni ln gamma I. And when it is a binary system, we can write minus R into N1 ln gamma 1 plus N2 ln gamma 2. Okay, we can modify this equation depending on the number of constituents. So we got the expression for excess entropy. Now let us see how to find out the expression for excess enthalpy. Okay, we know there is a well-known relation between the excess Gibbs free energy GE and excess enthalpy HE. Excess enthalpy is represented by HE, H superscript E. This expression, right, dou by dou T of GE by T is equal to minus HE by T square. This is similar to the other expression. Do you remember dou by dou T of mu I by T was equal to minus H bar, partial molar enthalpy by T square, right? So similar to that, excess functions also can be expressed like this. Excess free energy by T, dou by dou T of excess free energy by T is equal to minus H excess divided by T square. From this expression, we can isolate HE onto the left side. So excess enthalpy HE is equal to minus T square into this T square comes here, a negative sign also. So minus T square into dou by dou T of GE by T. So minus T square is kept here, then dou by dou T of, instead of GE we can write down directly the expression for GE, that is RT sigma Ni ln gamma I, then there is a T here by T. These T's cancels out and we have this R can be taken out. So we have minus RT square into dou by dou T of what is left, sigma Ni ln gamma I, minus RT square into dou by dou T of sigma Ni ln gamma I. So the expression for excess enthalpy is minus RT square sigma Ni dou by dou T of ln gamma I. Sigma Ni is taken out. Minus RT square sigma Ni dou by dou T of ln gamma I. We have to differentiate ln gamma I by I with temperature. So for binary system we can write excess enthalpy H is equal to minus RT square common factor into N1 dou ln gamma 1 by dou T plus N2 into dou ln gamma 2 by dou T. Just expanding, right? Just be expanded as in the previous cases. This is equation 4. And the excess enthalpy HE is same as the enthalpy of mixing, because we know delta H mix in the case of ideal system it is 0. We had proved it earlier, right? Delta H mix in the case of ideal system is 0. So delta H mix real will be equal to excess enthalpy, because any excess property is the difference between mixing in the real case minus mixing in the ideal case, and mixing in the ideal case is 0 here. So excess enthalpy is just equal to delta H mix of the real system. Okay. If the heat of mixing, that is excess enthalpy, is 0, it is not necessary that the solution should be ideal. Okay. So if this value, this equal to 0, that doesn't mean that the solution should behave ideally. Solution behave ideally means gamma I has to be 1, right? So when gamma I is equal to 1, normally ln1 will be equal to 0 and these terms become 0. But this value of gamma can be less than 1 or greater than 1. Any value is possible. It doesn't restrict the value of gamma I to be 1 for excess enthalpy to 0. Why it is so? Because here we have the derivative dou by dou T of ln gamma I, dou by dou T of ln gamma I, and this activity coefficient is independent of temperature. So anyhow, this dou by dou T of ln gamma I will be 0. So okay, so gamma I can have any value. It is not because it is 1 this term becomes 0, but it is because gamma I is independent of temperature. That's why this term becomes 0. Okay, so remember, gamma I can be equal to 1 when it behaves ideally, or it can be less than 1 or greater than, whatever it is, delta H mix will be 0, and hence excess enthalpy will be equal to 0. So accordingly, the solution may show positive or negative deviation from ideality, and it may not obey Raoult's law. However, if the solution is ideal, then gamma I is equal to 1 and ln gamma I is equal to 0 for sure. Okay, hence He must be equal to 0. Similarly, for excess volume also it is equal to 0 when activity coefficient is independent of pressure. Here when activity coefficient is independent of temperature, He becomes 0, and in the case of excess volume, when activity coefficient is independent of pressure, excess volume becomes 0. Okay, so remember this expression, and depending on the condition, gamma L and gamma I may become 0 or not. Depending on that, He can be 0 or not. Now let us see excess volume VE. And excess volume VE can be, Vxs can be expressed as Vxs is equal to dou Gxs by dou P at constant temperature. Okay, now we can substitute the value of excess free energy Ge, and since RT is a constant, we can take that out. So the rest will be dou by dou P of sigma Ni Ln gamma I. RT sigma Ni Ln gamma I was the expression for Ge, right? From that we took out the constant terms RT outside. Then dou by dou P of sigma Ni Ln gamma I, which is equal to RT sigma Ni. We took sigma Ni also outside. Then dou by dou P of Ln gamma I. Then for a binary system, excess volume can be represented as RT into N1, the first component, right? N1 dou by dou P of Ln gamma 1 plus N2 dou by dou P of Ln gamma 2. Okay. But we know, we have already proven that delta V mix in the case of ideal system, ideal gases is equal to 0. Okay. So what will happen? Excess volume VE is just equal to delta V mix in the case of real system. And imagine if this delta V mix is equal to 0, what would that mean? If excess volume is 0, if delta V mix real is 0, then excess volume is 0, right? That means the activity coefficient is independent of pressure. Here it is dou by dou P of Ln gamma I. So as we have discussed in the case of excess enthalpy, here VE becomes 0 because this term activity coefficient is independent of pressure. It is not compulsory that it should behave ideally. That means gamma I is equal to 1. It is not restricted that gamma I can have only the value of unity, but it can have any value, but it becomes 0 only because Ln gamma I or gamma I is independent of pressure. Okay, so remember all these expressions of excess functions, and in all these expressions it is, you can see that it is related to the activity coefficient gamma, right? Excess chemical potential or excess Gibbs free energy, excess entropy, excess enthalpy, excess volume. In all these excess thermodynamic functions, finally we can see it is dependent on or related to the activity coefficient gamma.